Hi, in this video, we want to take a look at statistical analysis of spatial point processes. Okay, so we've got events in a spatial area, so on the ground, and we have their coordinates, probably their latitude and longitude, and we want to analyze the points from a statistics point of view. All right, so we've got two types of properties that we're interested in, first order and second order. First order tells me about the distribution of the events, and second order tells me about the interaction between events. Okay, so first order properties. This is the distribution of events. There's two ways to really tackle this. The first way is to study the spatial distribution. So we're going to be studying the spatial density of the points, much like, and we're going to treat the situation like we would with density estimation, just like in like bivariate statistics. All right, another thing we can do is investigate the intensity of points in the area, and we're going to call lambda the intensity. So lambda of A is equal to the expected value of the number of points per unit area, given that our point is in the area of A. All right, so now for the second order properties, we're interested in the interaction between events, and we could have clustering. So if I see a point, the probability distribution around that is going to be like greater there. Regularly spaced, it's like things are getting pushed apart, like there's competition between events, or they're uniform where we have neither. All right, so here are some assumptions that we make for this. First and foremost is that the overall distribution of events is over a larger scale, and I don't have to worry about small scale aspects of this, but interaction is on a small scale. So this is important in that when I talk about interaction, if 2 points are far apart, I'm going to make the assumption that there's no interaction between them. Now, far apart will depend on, when I say far apart, what is far, what is near, will depend on the situation you're looking at and the events. All right, so what we're going to do, we're going to take a Poisson point process, and we're going to assume that events occur independently and are distributed according to a given intensity. All right, so we've got two ways to tackle this. We have homogeneity for a Poisson point process, or we have inhomogeneous or heterozygous point process, Poisson point process. Right, so with the homogeneity, we're assuming that our intensity function is constant over our sampled area. Okay, so our game plan from a statistics point of view is that we're going to make the assumption that this is correct. Then we compare the assumption to our data, and then we can reach a conclusion based off of what our theoretical model is and our observed data. Now, if I want to assume that that's not correct, things get more complicated. We're not going to talk about that in this video. All right, so let's talk about homogeneous Poisson point process. So all events are independent and uniformly distributed. So if I look at the points in any given region, it's going to look like uniform distribution of points. The location of one point does not affect the probability of other points appearing nearby, and there are no regions where events are more likely to appear. Furthermore, the process is stationary and isotropic. Okay, so the number of given events in area A, or I should say region A with area A, is Poisson distributed with mean lambda times A, where lambda is the constant intensity of the point process. Okay, so this is similar to what we see for Poisson distributions over time intervals, but now we're dealing with an area. And given in observations in a region, they are uniformly distributed in A. Now, when it's not homogeneous, then we can have non-constant density, or we have and we have independence between events still hold. So for the Poisson process, we're going to assume that when it's not homogeneous, we have non-constant intensity, but we still have independence. All right, so let's estimate the intensity. All right, so for homogeneous point process, remember, we're going to use this one to figure out what's going on, because this is going to be our benchmark to compare against our data. All right, so we're going to take our expected value, which is just the integral of lambda over the region. And so since lambda is constant, I can factor this out, and boom, it's just lambda times the area of A. Easy peasy lemon squeezy. All right, well, very naturally, an unbiased estimator of the intensity when it's homogeneous, it's just going to be number of points divided by the size of the area. As simple as can it be. Now, things get a little bit more interesting if it's not homogeneous. All right, well, in that case, we can estimate using a density point of view. So we're going to figure out an empirical density just like you would with regular old univariate data. So the kick here is that it's going to be bivariate. It's got 2 dimensions because I'm going to have latitude and longitude. All right, so the important part here, first thing to focus on is on this kappa. All right, so this kappa is going to be a bivariate and symmetric kernel function. This is the kernel function of our density estimation. Q compensates for emptiness around the border. So when I get to the boundary area, what's going to happen is that, well, at a certain point, I stopped sampling. I didn't go, I didn't go so far out, and past a certain, sampling region, I have no more points. All right, so what that would do, that would make the region look like it has lower density than is appropriate. This Q is designed to compensate for the fact that we have no points beyond our sampling region. H controls the amount of smoothing. All right, so H is here. Large H will give very, very smooth and possibly univariate distributions, while small h will give us very spiky and lots of peaks. So if I make h very, very tiny, what I'm going to see is, like in my density, there's an explosion right around every point, but then I'll have like valleys in between on my density. If h is very, very large, it's going to look like kind of like a dome. All right, so for the kernel functions, the two that are presented in the textbook are the quartic or biweight kernel and the Gaussian kernel. And so here, what we're doing is we're taking the distance of other points from the reference points, and we just drop it into this function. Now we realize that u is a point on the ground, so I'm going to have the the first and second coordinate values in there for the norm of the distance. And then the Gaussian is very simple. Oh, now something I dropped on this, I made a mistake, is that u has to be less than 1 in magnitude. So we're only in a certain region. Beyond a certain region, this kappa function takes the value of 0. So that is an error on my part. All right, so let's go ahead and look at an example of visualizing the density. All right, so what I'm going to do is I'm going to take some points. I'm going to randomly generate some points. And then I'm going to get a Gaussian distribution for each one. And then I'm going to combine all those Gaussian distributions into one bigger distribution. And the best way to describe this is with the picture. All right, so what's going on here is each of these black dots is a point in my data sets. Now this is, univariate, but the point still, or the description still works. What we're going to do around each individual point, I'm going to take a Gaussian curve. All right, now the h corresponds to how wide or how narrow I want this to be. All right, so here, this is the Gaussian curve for that point. This curve is for this point. Over here, I have this Gaussian curve. And so what I do, if I add up the value of these curves, I can get a curve going for the entire distribution. And now what I could do is if I made H very, very tiny, what would happen is my density would be flat, 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 explode, flat, explode, flat, 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 explode, explode, flat, explode, and so on. If I made H really, really big, what would happen is that each of these individual Gaussian curves would get wider, and the whole thing would look more like just one flat Gaussian curve. All right, so let's go ahead and run an example where we want to look for kernel smoothing. So I want to know what's the best parameter for working with this, for choosing my smoothing out. All right, so what I'm going to do, I'm going to take the Redwood full data sets. So here is the spatial points of Redwood full. Those are loaded in this document in a previous video. And take the coordinates, convert them to points in the SPLANCS package. And here is the points for the polynomial region for the boundary. And then the number of mean squares errors I want to look at, and here's the range of values. And when it computes this, I'm going to have a minimum, and I'm going to have a whole bunch of different mean squared errors. What we're going to do, we're going to take the one that is the smallest. So I'm going to take the mean squares error. I'm going to find the smallest one, and then I just extract that H. So this code here takes several different H's and computes the mean squared error for each one of those. The one with the least mean squared error gives me the H that I want to use for this problem. And so we see 0.04 looks like a good choice. All right, so let's go ahead and cross-validate this using the Diggle method. All right, so what I'm going to do is I'm going to convert that spatial points of my Redwood to a point process, a Poisson point process. Then, so that is the computing of that. Then I go through, run the Diggle algorithm on it, and then I need to convert that to numeric, and I see that here it says 0.02 is the optimal bandwidth. All right, so 0.02, 0.04, you know, I might want to play around, see what feels best for my process. All right, so now let's go ahead and visualize the mean squared error of the density estimates. So I want to check and see, are these good values? Are these reasonable? All right, so what I'm going to do, I'm just going to take the mean squared error and the bandwidths I previously computed. I'm going to plot them, and let's see what we get to see. All right, so when I use the coordinate kernel, we see that it comes down. As I make the bandwidth larger and larger and larger, the mean squared error is coming down pretty fast, and then it stabilizes. All right, so any value in this flat region is reasonable. Now there is a minimum, and this minimum is around here, but I could reasonably have taken any value along this flat region. I personally probably would choose one closer to a smaller value off of this. And I got that point just to visually see using which.min to extract that. And then, you know, I get the minimum, and then I extract that H, I extract that MSE, and then I plot that point. All right, so now let's do it again, but this time I'm going to do it for the Gaussian kernel. Okay, so I'm going through exactly the same process. And I can see that, hey, this comes out to be about 0.02. All right. Now, which one to use, bi-weight or Gaussian, is, you know, is a judgment call. If you are, you know, if your subject matter experts have a preference, you know, go with either one. I would lean towards Gaussian just because it has a lot of theoretical justifications why it would be good, but it would be reasonable to use the byweight also. All right, so now let's go ahead and take a look at creating a spatial grid. All right, so first thing I'm going to do, I'm going to set up my polynomial region that I'm going to be plotting. So these are this is like the bounding box of where I'm going to be plotting. I'm going to create a spatial grid in Map Tools. And I'm taking the points I have for my redwood data, and then I'm going to take them. So those points are scattered all about. What I want to do, I want to get a grid of values over the entire sample region and get an estimate of what the density is going to be. And so by doing this, is my first step in converting my data points into a density estimate over a grid. And so now I'm going to extract the grid from Map Tools. And here is the summary. So now I have a grid of values. So here is the cell center, offset, cell size, and the number of cells I have in each direction. All right, so I have 100 by 100 grid. Now what I want to do, I want to go through and I want to estimate the kernel in 2 dimensions. I'm going to use the SPLANCS package. I'm going to use the spatial kernel 2D. I drop in my points. I specify that polygon that I already put in, and then I specify the grid. So this specifies the values I'm actually interested in for to estimate. And here I'm taking a reasonable bandwidth for my estimation. And we can see that we've got several of these. And now I can see the outputs from my spatial grid data frame. I want to show you the output of this. I want to skip down to this because it'll make more sense here. All right, so here, this is the output of all that code, all that work. Visually, so you see when I have a very narrow or very small bandwidth, what's happening is that these white values, the density is practically 0. Then at these little tiny circular points, it's exploding super big. Now so these are, I can see where the points actually are. If I make the bandwidth a little bit bigger, I can see that the practically non-zero region around the point is a little bit bigger. If I make the bandwidth even bigger, they start getting larger and they start bleeding into each other and they start smoothing out. And when I get them super large, now it's very smooth. And if I made it much larger, it would just look like one solid color. And we see the same thing for Gaussian and for quartic. All right, so let me go back to explain what's going on with each of these now that we see the visual outputs. All right, so for each of these, we're going through for the quartic density. And we're just estimating with the appropriate bandwidth. And to keep everything nice and neat, I'm just making it into one data frame. And then for my spatial grid data frame, what I'm doing, I'm taking the grid I already built and I'm taking the data frame and I'm putting them together. By how I constructed this, by having the grid inside here, since the grid is inside the kernel aspect, this grid is going to perfectly match up with the data I have. Boom, I've got everything set up in one nice, neat package to be able to start doing my statistical analysis. This format is treating each of these different densities as a different variable. When the computation here is that we have all of them are based off of the same data, but potentially I could have 4 different variables each with their own density for the situation. Now I can do exactly the same thing for Gaussian. I just need to convert over my spatial points to a point process. I need to specify my standard deviation and my dimensions. And this XY was defined earlier. Then we just go through and estimate our densities how we want. So here, I'm specifying my density. And then I store the outputs in my spatial grid data frame. And remember, the spatial grid data frame was already defined in the code above for the quartic, the bi-weight. And now I have everything all nicely together. So now to visualize the distributions, what we're going to do, we're going to use the R color Brewer package, Brewer palette. And the author chose red because redwood makes sense. N for the number of distinct colors. And then this is all about just plotting with SPplot. And here we can see the output once again. All right, so that gives us a way to visually look at what's going on with my data. And I can see, what density would be appropriate. For me, I would probably go with Gaussian 0.05, just off of this. It's not too spiky, it's not too smooth. I feel like it's a balance of the 4 Gaussians. And if I was to go with the bi-weight, I would probably pick 0.1. Now let's look at the likelihood of our non-homogeneous Poisson process. Okay, so if it is homogeneous, that's easy peasy lemon squeezy, but what we want to do, we want something a little bit more flexible, something that can handle a wider range of situations. So what we're going to do is I'm going to take my likelihood function. The likelihood function is going to be the sum of the log of my x's minus the integral of our intensity function at each location within my area that I'm concerned about. And this simplifies down to the sum of the log of x's minus the expected value of the count within area A. All right, so our log linear model is that the log of lambda of x is equal to the sum of coefficients times covariates at the location. All right, so here, this is the location that I'm interested in. This is a covariate variable at that location, and here is a coefficient connecting the covariate to the intensity. So my z of j is a covariate at the location, and beta is a coefficient of that covariate. Now, our log intensity model is going to be very similar to generalized linear models, where I'm taking log of lambda is equal to intercept times a term for first coordinate, second coordinate. There should be a plus sign right there. Then a square term plus another square term plus an interaction term. So let's go ahead and run an example. Let's take a look at this. Now, all this code here is all about just working out the details. What this is going to do, this is going to use adaptive integration from the cubature package to work out the details of this for us. That way, I don't have to go there, pencil and paper working this out. And the optimization is to minimize on this. So let's go ahead and load the maple tree data. And so I'm going to get my data set of Lansing from the stat data package. I'm going to limit the data to the maple trees, and then I'm going to convert it to points. All right, I played around with this, and so the author started with this vector for the initial parameters, for the initial coefficients. I wanted the R Markdown document to compute fast when I hit run. So what I did, I figured out the coefficients on my machine, and then after it converged, I slapped it into here. And so here are the coefficients. So here, this is the x1 coefficient, the x2 coefficient. This is the minus, or so this is the x1 squared, x2 squared, and then we have interaction term. Oh, sorry, no, this is intercept, x1, x2, x1 squared, x2 squared, and then interaction. And the optimization function will figure out this for us if we pass this to it. Now, the author's number of iterations did not converge on my machine, so I cranked it up to 1,000. So let's go ahead and visualize what we've got. So I'm going to define my grid topology using the SP package. Here is my cell center offsets, cell size, and my dimensions. So now I'm defining my intensity function this way. So I'm just dropping all the values in. And remember, I'm using the optimized values for this. So this is my intercept, and this is all other coefficients. Now I'm defining my spatial grid data frame. So I'm taking the grid that I've already got, and here is my data frame where I'm taking intensity is equal to lambda at each of the points in my grid. Now here are some plotting parameters to use inside the SP package plotting function. And so that list appears down here. I'm going to use a color ramp palette for reds, which I had defined earlier. And so now let's take a look. All right, so we can see that the dots, these dots are being plotted because they're the points themselves. So those are the spatial points, are the black dots. The color ramp is from going over the grid, taking the intensity of the, or the estimated intensity at each point. All right, so I can look at this. And I kind of see like a gap here, a gap here, a gap here. So I am thinking that there might be some clustering going on this one. All right, so now let's go ahead and compute some confidence intervals. Now, this PPM function, you can think of this as like the spatial version of generalized linear models. All right, so my log intensity is going to be this form. This is my formula of x plus y, x squared, y squared plus interaction term. And when I run this, I get estimates, standard error, and I get a confidence interval, and I get, z-scores for hypothesis testing, and we get to see which ones are statistically significant. All right, well, I looked at this and I went, you know what? I have 3 terms that are not statistically significant. I should remove one. So what I did backwards elimination off of this. I eliminated this one first. Then the next one I eliminated was this. And honestly, I would have been okay with stopping at that point, but I went ahead one step further and got rid of this one also. So my reduced model is x. Oh, sorry, no, never mind. I went to x plus y plus x squared. All right, so x plus y plus x squared is my model. Let's take a look. Does that look reasonable for this? So I would have, something going on with x. So that I would have quadratic, and y is also involved. So you'll notice that things kind of look thinner up top on y. So y is probably involved. And to my eyes, I do kind of see, especially with these color bands, something going on in terms of x squared. And I see it would definitely have like a negative coefficient going on. And so here is my reduced model, and you notice that everything is statistically significant. Well, here I only had 3 statistically significant. Now I have 4, which is typical of backwards elimination. Now let's talk about second order properties. Second order properties, I'm interested in interactions between events. And when I'm talking about interactions, I'm either talking about clustering, where things tend to be grouped together, or competition, where they tend to be far apart. So clustering, for example, could be sickness, because if I sneeze when I'm sick, you get it, like we live together and people in my neighborhood get sick because we're all proximal to each other. Competition, think of like animals that have territory, and they try to stay out of each other's territory. There they spread out from each other because there's a competitive aspect. All right, so if I have a homogeneous Poisson process, then my kappa function is going to be 1 over lambda times the expected value of the number of events in the in a radius of size s around the point. And so for homogeneous, this will just be pi r squared, easy peasy lemon squeezy. Now, if, oh, sorry, this formula here, this is Ripley's unbiased estimator. This is a little bit more complicated, where these W's are weights. And this is the count of points within a radius of another given point. Here is the size of the area, and divided by the number of points times number of points minus 1. If these two are far apart, that is evidence that I do not have a homogeneous point process. That would, so if these two calculations differ by quite a bit, then I would conclude that I would have clustering or I would have competition. Usually S is small. And if I have very few points around another point, so if the number of points within a radius is small, then that is evidence of competition. If the number of points within a radius is large compared to what I would expect, then that is going to be evidence of clustering. All right, so now what we can do, we can go ahead and do a simulation to try and get an estimate of what's going on with this. So what I want to use, I want to use the KS function that we talked about in a previous video. And I would just want to check to see if I run through this, I do some computations, what do I see? How does each of my 3 samples, do these match up to the homogeneous assumption? All right, so we're going to do this for the Japanese pines. We're going to do this for the redwoods. And we're going to do this for the cells. And so we're going to run the envelope function in the stat core. I need to convert my spatial points to a point process. The function is KS. R was defined in previous code. See, that is in a previous video, I believe. The N rank is 2, and we're going to do 99 simulations. And so when I get my outputs, I'm going to put everything into one big result, into one data frame, and then I'm just using cbind, easy peasy lemon squeezy. All right, so I'm putting all of the simulation results in a data frame, and then I'm in stacking on top of each other. Then I'm indicating which simulation each point corresponds to. And now I'm just going to go through and plot what's going on. So I'm going to use XY plots from the last package. And I'm going to take my observed minus my theoretical. Here is my data. It's going to be a line type. And we're going to have 3 panels, 1 for each of the data that I'm interested in. So I'm going to have a polygon showing like my what I would expect to see, like a kind of a boundary region. And then here I'm going to plot lines to show what's going on. So the polygon show if everything was according to the assumptions, I would expect my line to stay inside this horn, but it's clearly not. Here, so this is the difference between my estimated value and my theoretical value. Here it looks like the Japanese does not have clustering nor independence. And so see here, this is negative. So we see that we have fewer points in a region than expected. Therefore, this is evidence of competition. Here, this is evidence of clustering. All right, well, that's all I've got for you. Take care and goodbye.